All right. Yeah, so today I'll be talking about Hecke polynomials in the Legendre and Kloosterman family. So this is kind of a project that I've been doing for a while now, and kind of the motivation for the project that I won't actually get to until much later in the talk, and I'll kind of tell you what the motivation. I'll point out why I was motivated to do this stuff in the first place. But again, that's about maybe more than halfway through the talk. Oh, sorry. Okay. Sorry, I can't click back and forth between the talk. I'm sorry, hold on one second. Let me, maybe I'll just do continuous scroll. Let me see if that'll work. All right, I think that works.
Yeah.
All right, sorry about that.
No problem.
All right, so first I'll start with the Kloosterman family. So you can see Kloosterman there on your right. And so this is defined to be an exponential sum given here. So if t is element of a finite field, then you can define this exponential sum here. Zeta p is a primitive p through the unity, and the exponential sum is this x plus t over x. And so notice that here the parameter m can change, so the field can grow, and so this gives you a sequence of exponential sums. And to study those exponential sums, that sequence, you can plug it into this generating function, this L function. And it's classically known that this L function here turns out to actually be a quadratic polynomial. So it has two roots, or two reciprocal roots. And one may ask, well, how do these roots vary as the parameter t varies? And so there's, right, so for different t, the exponential sums change, and then these roots change, and you want to know how this varies. This is a little bit, so there's various ways to try to answer this question. So I'll mention two of them, but I'll focus on a third. And so, so here's the L function again. Here's the two roots, and one is an analytic variation. And that turns out that for this Kloosterman family, one of these roots, and I'll focus here. I'll say it's this pi 0 is a p-adic unit. It's always a p-adic unit, no matter what t you plug in. It's always has a p-adic norm being 1. And so it turns out that this unit root satisfies this formula here, where you take this quotient, f of t over f of t to the p, where f of t is this hypergeometric, or this confluent hypergeometric function given by this. And so this function here, in some sense, describes this hypergeometric function describes the variation in some sense of this unit root. That's one way to kind of, you could read this formula. So that kind of helps describe some of the variation. Another way to describe variation of the roots is by angles. And so it turns out that the Kloosterman sum is the absolute value of the Kloosterman sum is bounded by 2 to the square root of q to the m power. So it's bounded by this amount here. So when you take the quotient of this, you get a number that's between -1 and 1. Oh, also Kloosterman sums are real numbers. These are real numbers. So this is a real number, and it's bounded between -1 and 1. And so this is equal to cosine of some angle. And so as the m varies, these angles will vary. And as the t varies, the angles will also vary. And the question becomes, how, so you get this set over all m and over all t of angles, and the question is, how are these angles distributed in between 0 and pi? And it turns out their distribution satisfies a Sato-Tate distribution, which is this one here, where if f is a continuous function, and you take this integral here, then with weight sine squared, you get that that it's equal to this averaging of the function evaluated on these angles, these Kloosterman angles here. And so again, this also tells you something about the distribution of these Kloosterman exponential sums as t varies.
Before you go on,
yeah.
In your analytic formula, the thing you call pi squared, is that Dwork's constant pi, or what pi?
It is actually Dwork's constant. That's correct.
Okay.
Yeah,
all right.
Yes, it is.
It's not 2 pi I. I mean, it's not.
It's not 2 pi I. Yeah, and I meant to actually say that, and I forgot.
Okay, no problem. I was just wondering.
Yep. And actually, I forgot to also point out this formula is a little simplified. This quotient, it's a little bit, it can be a little bit more complicated than that. I'm actually writing a slightly simplified form of it, but it's, this is essentially it. And also, my kids are home from school, and so I'm going to do my best to, over that. All right, so another way to study this variation is by looking at symmetric power L functions of the family. And so here I want to focus on this line here, the symmetric power. And so here, this product is the symmetric power. You see the pi 0 here and the pi 1. These are the roots to k minus r to r. And then the product, you're making an L function by taking the product over all the parameter t over closed points of the algebraic torus over fp. Right, so this is basically gathering together all of the entire family together into one package and creating this a new L function. It's known that this is a polynomial with coefficients over z, not from this, but with some theory. And in fact, this polynomial can be factored into certain pieces. So there's a 1 minus t factor. There's a finite product of terms of this form, so plus or minus p to the k over 2. And it's known exactly how many positive ones there are and how many minus ones there are, so this is known. And also this mk is another factor where mk is pure of weight k plus 1 over 2. So all of its roots have absolute value a square root of q to this power here. There's also this mk satisfies a functional equation, which with this weight. And there's also, what's also known about this mk here is that there's a lower bound for the p-adic slopes. And so for all p greater than or equal to 3, this lower bound for the Newton polygon is known. And so I'm stating a bunch of people's work here right now. And so I just mentioned that right now. This is not in, this is kind of alphabetic order versus timeline. It was first studied by Roba, and then by Fu and Wan, and then myself, and then Yoon studied it for e is equal to 2, and then some more recent work is for Son, Saba, and Yu on this. So it's kind of a combination of a few people's results. All right, so this is again trying to understand the variation with respect to the as a variation in t. So what I want to mention is that the start of something is that I want to give a modular interpretation in the case when the prime p is equal to 2 or 3. So this is kind of it's a specialized case when the prime is p is equal to 2 or 3. We'll talk about that a little bit more. But here's this again, symmetric power L function. Here's the factorization that I mentioned above. And to describe the theorem, to describe this modular interpretation, so let gamma be a congruent subgroup of SL2Z. And we denote by SK of gamma the space of cusp forms of weight K of level gamma. And we're going to let UP denote Atkins' U operator. Then the result is that when P is equal to 2, and you let gamma be this congruent subgroup, gamma 1, 4, or you let P is equal to 3 and you let gamma be gamma 1, 3, this congruent subgroup, then you get this equality here, which is a modular interpretation. So it's so on the left-hand side, you have the L function, this Kloosterman sums, and on the right, you have Hecke polynomial. So this would be the Hecke polynomial. But here, notice that the weight is k plus 2 versus this is the symmetric power is k. Right. And so just to kind of mention kind of some of the ingredients for this proof of this theorem. One is that for a fixed S, if you try to count how many Kloosterman sums, if you change t, you let the parameter t change, how many Kloosterman sums are equal to this fixed S, this fixed number? How many of them are equal to that? And it turns out that that number of Kloosterman sums that equal this number is equal to the Kronecker class number on binary quadratic forms. You got this equality here. And that only happens for p is equal to 2 and 3. It's not, I don't know what happens when p is 5 or larger. So I don't know. I don't know what to do about that. Now, I didn't prove this. This is not my proof. This is, so for p is equal to 2 or 3, this is a proof by Katz and Livne. But it was also proven independently by Schoof and Van de Klecht. And for p is equal to 3. And for p is equal to 2, I'm sorry, for p is equal to 2, they did that. And for p is equal to 3, you can go through the same proof that they did to do this. And so anyway, this has come up a few times independently by people. But again, nothing for p is equal to 5 or larger. Although I have to say that I did look at the frequency of these things for p is equal to 5 or higher, and there's definitely some nice distribution going on. I don't know how to describe it. It's not described in the same way. Okay, that's one. And then 2 is you can apply the Eichler-Selberg trace formula to this Atkins operator, and combining step number 1, you get this equality right here. So that's the ingredients of the proof for that.
Can I ask a quick question real quick?
Yeah.
How does this determinant work? Sorry, I'm not familiar with Hecke polynomials.
Oh, so this is, I mean, I'm not quite sure of the question, because it's, so this cusp form is just a finite dimensional vector space.
Right.
UP is just some linear operator on this space. So it's just
okay.
this, a characteristic polynomial.
Okay.
Yeah. Just so it's
quadratic forms, s squared minus 4q, is that positive or negative, or doesn't it?
It's negative.
It's
yeah,
a negative.
this is a positive definite. Say again?
Okay.
Yeah. Yeah, it turns out this s squared, this s here is always smaller than 4q.
Okay.
So, yeah. Yeah, so for p is equal to 2 and 3, this is, yeah, this is always negative. All right, so that you can actually break this down a little bit further. So up here, notice I had this 1 minus t, you know, the L function of the symmetric power has this factorization, but you don't see that here except for this 1 minus t popping out. So you have, here you can break this down even further, and that's this next part, is that when p is 2 or 3 or k is even, then you can see this factorization. In fact, that this mk here is this Hecke polynomial, where this is the Hecke operator acting on cusp forms over SL2Z, and this one here, this product where it's p to the k plus k over 2, this factor is coming from the space of new forms on gamma 0p, and so this is just Atker-Lehner theory applied to that previous theorem, and just with some so you can refine the previous result to get this. When k is odd, this disappears, and you just have you only have when k is odd. Sorry, just go up. When k is odd, this is all you get, and you don't have this middle term. So that's why it says k is even. The k is odd is so both k even and k odd are both known. It's just k even refines into something more interesting. So that's why this is here. All right. All right. So this is kind of going in a slightly different direction, but I want to let me go back a second and mention here this. So I'm interested in p-adic slopes of L functions, and so these lower bounds are something that interest me. And you can see here that p greater than or equal to 3 was known, but there's nothing for p is equal to 2. And so that wasn't known. And so so I want to mention kind of a roundabout way for me to be able to get the p is equal to 2 case of this lower bound. And so it brings up some other theory. So that's the motivation of why I'm going to do the following. So I'm going to talk about now p-adic symmetric power function L functions. All right. So now, not talking just about p is equal to 2 or 3, but take p to be any prime, and then fix kappa to be a p-adic integer. And then take a sequence of positive integers that are tending to infinity, but at the same time, their p-adic limit is kappa. So positive integers tending to infinity, but the limit is kappa p-adically. Then it's known that if you look at the limit as I goes to infinity of these symmetric powers, the L function of the symmetric powers as ki. So the symmetric powers are growing, but they're growing p-adically in some senses. But they're positive integers going to infinity. So this L function is getting larger, because this is a polynomial, but its degree is going to get larger and larger and larger. So it's getting bigger and bigger and bigger. This limit is going to exist, and in fact equals the following. It's equal to what we call, or I call, the kappa symmetric power L function. And so just to differentiate it from the previous symmetric power, I put a little infinity sign here to represent that it's kind of like the limiting object of kappa, and it's equal to this product. But here the difference is that before, for the symmetric power, the index I went from 0 to k, but now the index is going from 0 to infinity. So it is different. And I want to emphasize here that even when kappa is a positive integer, this does not reduce down to the usual finite, like symmetric power. That this is actually a different beast, because this infinity will stay there no matter your kappa is a positive integer or not. And so this is right. So this is, if you take limits of these finite symmetric powers, you get this this p-adic symmetric power. And a few years ago, I showed that you could expand Dwork's p-adic cohomology theory to create a cohomology theory for the objects of this type. And so this is a theorem that basically saying that such a cohomology theory exists for this object. And so here, you know, this is just giving that this L function is this quotient. I want to emphasize that this type of object here, this type of L function, is not expected to be rational. This is supposed to be purely p-adic transcendental. This H1 here is going to be an infinite dimensional vector space. This H0 may not be, but the H1 is expected to be. And so this will be a p-adic meromorphic object. And then also known that for every non-zero kappa, the H0 is actually equal to 0. And so the bottom is actually not there. And so this L function is in fact p-adic entire.
So when you actually look at the case kappa as an integer, can you see that from this kind of p-adic entire function? I mean, when kappa is an integer, you can go back to the symmetric power, right?
You can't. No, it's actually different. So when kappa is a positive integer, when kappa is a positive integer, this is still expected to be infinite dimensional. There won't be the finite symmetric power. They'll be different.
So it's not like some kind of deformation or something?
It's not a deformation. Yeah, it's more like a boundary. It's more like a circle where your the finite symmetric powers are kind of in the center, and then these things here lie on the boundary of it. And so even though, yeah, so that's why I denote this. I have this infinity kappa to differentiate, so that it really is different. Right. So we can apply this theory here to the previous, the case where the L function of the case symmetric power, sorry, the Kloosterman family, when p is equal to 2 or 3. And so this is a corollary of that previous theorem, which basically says that that these infinite, like p-adic symmetric power L functions, when p is equal to 2 or 3, is in fact equal to the Fredholm determinant of the UP operator acting on S kappa dagger. So this S kappa dagger is a space of overconvergent modular, p-adic modular forms of weight kappa plus 2. And so we get a relationship between, so before it was the modular interpretation was for L functions of finite symmetric powers. And what this is saying is that it's giving a p-adic modular form interpretation of this object here. And so when p is equal to 2, and this is the kind of some motivating factor for this, when p is equal to 2, it turns out that this has been studied. When p is equal to 2, the right-hand side has been studied, and someone computed that the p-adic, that the reciprocal roots all have can be ordered so that the p-adic norm is equal to p to the 2i. For I being 0, 1, 2, they know exactly what the Newton polygon is of this object. I wrote this in a kind of a different way than I wanted to. At the time, it seemed good, but what this is saying though is that is that the Newton polygon. So if I, sorry to jump back and forth. It's saying, what this is saying is that the Newton polygon this is an equality right here. Okay, not for this L function here, not for this K here, but for this p-adic symmetric power L function that you get for when p is equal to 2, you get this as an equality. And there is a relationship there. So even though these p-adic symmetric power L functions are not exactly the L function of the finite symmetric power, if kappa is equal to a positive integer, there is a relationship between the two, and that relationship will tell you that when p is equal to 2, that same lower bound for the Newton polygon that was mentioned above will also be true for p is equal to 2. And so for all primes p, that the lower bound for the Newton polygon is given by that one that was mentioned above, this one here. So actually, for all primes, this lower bound is true. But the way that there's this relation is for p is equal to 2, this is not necessarily in an equality, not necessarily. All right.
Just one question. If you expand out your L function for sim infinity kappa in powers of t, that's some kind of p-adically convergent. What ring does that belong to?
This one here.
Oh, yeah. So I guess it's a determinant. So it's a polynomial.
Oh, wait. So the right hand side is So the equality. This right hand side is so this is a entire function, but the left hand side is given by this Euler product, and so it's only going to be convergent on the open unit disk.
I see. So that's kind of like an analytic continuation of
exactly. It's exactly what this is.
So that's a convergent infinite product in some disk, which happens to be equal to this.
That's right.
Entire function that you've written down.
Right. So actually, it's a good point that you say. So here in this theorem here, this is kind of the more formalized, typical way of giving the p-adic continuation is that there's a cohomology theory, so that this L function can be written as these Fredholm determinants, and these Fredholm determinants are on this Frobenius here is Dwork's Frobenius. These are completely continuous operators on these Banach spaces, and so these will be entire functions.
I see.
So this will be p-adic meromorphic. So this gives you the more usual way of getting at the meromorphic continuation. But then this one here is saying a relationship that's atypical. That on the left-hand side, you basically have the exponential sums. On the right-hand side, you have cusp forms, and so it's saying something. I mean, I agree. This is definitely giving a continuation point of view as well. I'll just give a quick side note here that Dwork has some conjectures on something called the unit root L function. And I just want to mention this on the side in case anyone is interested. His unit root L function is defined to be this Euler product here, where all you do is you take the one p-adic unit root and you take the Euler product of all of those. You don't take any of the other roots of the family, just the unit root version. Then it's not hard to show that you get this equality right here, just from the definitions of these infinite symmetric powers here. So this equality here is just follows from definition. What the interesting part here is that when p is equal to 2, we get exactly what the Newton polygon is of this L function, which means for p is equal to 2, we get exactly the Newton polygon of the numerator here and exactly the Newton polygon of the denominator when p is equal to 2 again. And in fact, from this, you get actually there's no cancellation whatsoever. And so this is the first time that the unit root L function has had, that one of Dwork's unit root L function has been shown to have no cancellation whatsoever, and that and exactly what the Newton polygon is of the numerator and the denominator. The other results that I've seen on this it's just been approximations. Okay, so I kind of want to summarize some of the stuff we've been talking about so far. So here's the finite symmetric powers. And so here, one of the results was that the k symmetric power L function was equal to this Hecke polynomial, UP operator acting on space of cusp forms. Right? Now, typically, this is studied by looking at using some cohomology, either L-adic cohomology or p-adic cohomology. And so I specialize in p-adic cohomology, so that's what I'm going to focus on here. And so this left-hand side can be written as the determinant of the Frobenius acting on a p-adic cohomology space here. And similarly, this is true here as well with this kappa symmetric, this p-adic symmetric power. We have the Hecke polynomial again, or Hecke series in this case, Hecke series, and it's equal to again a Frobenius acting on a p-adic cohomology space. And this is actually where I started this project in the first place. Is that I understand these cohomology spaces very well, but I could not understand whatsoever how these p-adic cohomology spaces would produce cusp forms. See, the dimension of this space here of H1 is exactly this dimension here. Okay, -1. Okay, the 1 minus t. You know, there's a trivial vector here to get rid of, but basically the dimension here is exactly this dimension here. And so the cusp forms here and this H1 should line up somehow. We should understand how they line up. And same thing with the UP and this Frobenius. And I want to know how basically Dwork's p-adic cohomology theory can produce cusp forms. What's this relationship? And that's basically how I started this project in the first place. All right, so to talk about that, I want to bring up a different family. This is the Legendre family of elliptic curves. Let me see. It's 4:45. We started at 4:10. How long do you usually go for? Is it 50 minutes?
As long as you like.
Or until my kids get hungry and start to protest. All right, so this is the right. So Legendre family of elliptic curves, and so this is the Legendre family right here. So the parameter here is the t, and so it's given by this elliptic curve here. And so actually, before I move on, this picture here, this is the picture of Legendre that people thought was actually Legendre for 200 years. And it turned out that in 2005, I think it's 2005, 2008, I can't remember, I think 2005, it was figured out that that's actually not him. That it turns out, I think this is a lawyer or something from back then. It's not a mathematician at all. And it turns out that there's only one known picture of Legendre. There's only one known, and unfortunately, this is the only known picture of Legendre, which exists, and he's not the happiest fellow, I think, in this picture. Anyway, so that's Legendre, I guess.
After COVID-19.
Right. Oh. All right. So what we want to do with this family is we want to count the number of FQ rational points on this elliptic curve. So we denote that by the number here. And again, as m varies, as the finite field grows with m, we get a sequence of integers. We get a sequence of integers, and we can plug that sequence into a generating function, which we call the zeta function. This generating function, and it's well known that this zeta function of elliptic curves is a quotient. So it's a rational function. It is a quadratic in the numerator, and the denominator is explicitly given by this 1 minus t, 1 minus qt. And so again, you can ask various questions about how do these roots vary? You know, pi 0 and pi 1 vary as the parameter t varies. Actually, it's remarkable how similar these roots here behaves to the Kloosterman family. So for instance, in the Kloosterman family, I mentioned that there are a couple ways to study the variation of the roots. One is by looking at an analytic expression for the unit root. Oh, so it turns out there's a unit root here. As long as you're not at a super singular point, this is one of these is a p-adic unit, and it can be given in terms of hypergeometric functions. Also, the distribution of the you can create angles from these. Just like the Kloosterman, we created these angles and looked at the angle distributions. And these angles here also satisfy a Sato-Tate distribution, the same distribution as the Kloosterman as well. And also you can plug them into, and this is what I want to focus on, is plugging them into a symmetric power. And so here you're taking the L function is defined to be the product from I from 0 to k. So this symmetric product of the roots. And here you're also taking the product over the family where t goes over p1, but you're taking out 0, 1, infinity, and the super singular points for this product. All right. And so similarly to the Kloosterman family, this is a polynomial. Turns out this is a polynomial, and it can be factorized into 1 minus t to this. I put star here because sometimes it depends on the prime p. If this star is equal to 1, or it could be equal to 2, or it could be equal to 3. I think that's it. It depends on the factor p, or it depends on p. We have this factor here. Again, this is known. It's known how many pluses and minuses there are. It depends on the super singular points and p. And then we have this factor here, mk of t. And mk of t is known to be pure of weight k plus 1 over 2. It satisfies a functional equation. Its degree is known. And this was work done by, so Dwork gave a p-adic expression for this, a p-adic cohomology theory for it. And then Alan Adolphson in his thesis in 76 proved this part here, that it factors into 1 minus t. He gave these factors, and he also computed the degree of this, and he also proved the functional equation. So that was his PhD thesis, was the rest of this. And in his PhD thesis, he also conjectured the following, that this mk has a modular interpretation for k even. So for k even, it's this Hecke polynomial here, where it's the p Hecke operator acting on cusp forms over the principal congruent subgroup gamma 2. And this, again, so this is actually really where my interest started from this. I read his thesis, and I saw this conjecture, and two things came up for me. One is why why should this conjecture be there, or basically why, again, why are cusp forms showing up at all in this theory? And then 2 is why only even? You know, why even? And it makes sense actually. If k is odd, there are no cusp forms of odd weight for gamma 2. So this is 0. But mk is not 0. This is, I mean, not equal to 1 when k is odd. This thing's huge. When k is odd, this could be actually just a big polynomial. So I was like, what happens when k is odd? So I looked into this, and I found the following conjectures. The first one is that the k-symmetric power, it appears to always be a factor of this Hecke polynomial, up acting on gamma 1 for p. It always looks like a factor. Now, it's not equal. This has way too many factors to it, but it looks like it always has it. And the little star here means I have to ignore this term, this 1 minus t. So if you ignore 1 minus t, all of this stuff here looks like it's a factor of this stuff here. All right, that's 1. And then 2, he was not using the right group. He was using gamma 2, which has no odd cusp forms. But if you go to gamma 1, gamma 1, 4, if you go to gamma 1, 4, then you should have that mk of s is equal to this Hecke polynomial. So it's a bit kind of crazy looking, but it has the same flavor as before, acting on these cusp forms here. So this is a modular interpretation for all k. And also, I gave this to undergraduate student to help me get a lower bound for this, and with their help, we found, and so his name was Guowei Shan, and so we found this should be the conjecture for the lower bound for the Newton polygon. The only one I'm actually close to actually proving is this one right here, where there are some days where I have figured out the proof and I'm really happy, and then there's other days when I figured out my error. And but basically, I've come down to just the heart of trying to prove this, but I'm doing it the hard way. I'm not doing it with the Eichler-Selberg trace formula. I'll explain that in a second. All right, so these are the conjectures, none of which are proven. And so now I want to spend the rest of the time talking about why cusp forms are showing up. But I want to warn you. My warning is that I'm now going to be talking about how Dwork's cohomology theory is related to cusp forms. And it is, by nature, I have to get into some of the technicalities of this. And so it's a bit technical, and there'll be hand waving and so forth, but I apologize, but I'll try to do my best about trying to kind of explain a little bit about how cusp forms are showing up. And so this slide here is to just kind of give you an inkling of how it initially is showing up, of how these things are showing up. So we have this family of elliptic curves, ET. So T is the parameter of the elliptic curves, and attached to this is how does the cohomology vary? It varies by this differential equation here. This is the Picard-Fuchs differential equation associated to this family. And so this is, in some sense, so this Picard-Fuchs is giving a description of variation of the family with respect to T. So again, there's this, the variation is popping up again. This differential equation has 3 regular singular points, 0, 1, and infinity. And it has a holomorphic solution given by this hypergeometric, f21, 1/2, 1/2, 1. Now, if we let lambda be the lambda modular function, this is a universal covering map that goes from the upper half plane to the complex numbers minus 0 and 1. So here, it's taking away so notice that this is P1, but without 0, 1, and infinity. And so this is going from H to exactly the space where you're taking out the singular points of this. And now we have two groups. We have two groups going on. One, we have a covering map. So we have deck transformation group going on. And the deck transformation group of this covering map is exactly not this congruence subgroup gamma 1, 4, but a conjugate of it. It's a conjugate. All right, so that's the deck transformation group, but you have a differential equation with singularities. And so you can do the monodromy group of this differential equations. You can see what happens to the solutions as as the fundamental group wraps around these singularities, and that gives you the monodromy group of the Picard-Fuchs equation, and that turns out to be also this, the same group. They line up. And when these line up here, some magic happens. And so here's some magic, I'll mention it here. If you take this lambda modular function, this universal covering map, and you plug that into this holomorphic solution here, and so that's here. If you plug the universal covering map into this holomorphic, out pops theta squared, or basically what pops out is a modular form of level of with this congruent subgroup of weight 1. All right, so basically differential equations, universal covering map, and then out pops these modular forms. All right. So here, I'll mention a little bit of some of Dwork's cohomology a little bit. Sorry, actually not this slide. This slide is the functional equation map. So the L function of this the symmetric powers of this elliptic family can be described in terms of p-adic cohomology here. And here I put alpha, instead of putting Frobe, I put alpha here because I want to distinguish, I want to say that alpha is Dwork's Frobenius. And I'll mention that in a second why I'm writing it that way. So this is Dwork's Frobenius, and then there's this functional equation map on the p-adic cohomology where you're going, the functional equation map goes from the dual of H1 into H1. And it does the following. If you go into Dwork's work and you peel it apart and you understand what is happening, what is this theta, what is this functional equation map doing? So it does the following, that if you do theta of f and you get g, so say you do this, so f is in this dual and g is in H1, and you run this through Dwork's machinery, and out pops what is it really equivalent to? It's equivalent to plugging this function, this f as a function, into the kth symmetric power of this Picard-Fuchs differential equation. So you take this, there's such a thing as, if you haven't seen before, there's such a thing as taking a differential equation and taking the kth symmetric power, and out pops an even bigger differential equation. And you plug in f. And so you plug that into the differential equation. You don't get 0 when you plug into differential equation. It's not a homogeneous solution. You get this. You plug it in and you get w to the k times g, where w is the Wronskian of the Picard-Fuchs. All right, this I can't. If I was in person, I would square this off. This equation right here, I was reading a paper by Peter Stiller, and he was saying the following, that if you have a differential equation and you take the k-symmetric power of it, and you have an equation that looks like this, then you can produce cusp forms. And he gives you a way of doing that and why it works. And I can't go into that more detail because it's I mean, this is too much as it is. But basically, he gives you a way of going from the k-symmetric power of a differential equation to producing cusp forms. And again, this really only works when you have this special deck transformation equaling the monodromy group situation. When that happens, then he gives you this recipe, and it's very explicit. So explicit. Here is a polynomial that's in Dwork's cohomology, and in 2 lines of code in Mathematica, here's the cusp form that it produces. I just plug that into my into Peter Stiller's formula, and boom, cusp form. This is the explicit formula I was thinking about. How does Dwork's cohomology obtain cusp forms? And it's through, this is one way of doing it. Is doing this.
So his Stiller's result is a theorem or conjecture? I mean,
Theorem.
it's a theorem that
Yeah.
you get the cusp form of that weight.
That's right. Yeah, he tells you to, oh, you mean how to go from here to here? Or
No.
what?
So his result says that if you have this, what you said, that the deck transformation equals the monodromy, then you do the symmetric case power of this Picard-Fuchs differential equation.
Right.
You will get cusp forms of weight k out of it.
Yeah, he tells you a formula about how to get it. Just like here. Wait, where is it? Here. If you plug in this, lambda modular, this covering map into the hypergeometric, out pops a modular form. He has a formula that's like this, but more complicated, slightly more complicated. And you just look at it, and his formula works. I mean, he proves the formula works, and so and you just apply that theory here, and out pops cusp forms. Yeah, the difficulty was trying to come up with
number theory.
Was coming up with with this, seeing where this, and then coming across Stiller's paper as well. Was a bit of luck. So this is kind of half the story. This is talking about how H1, the cohomology, is related to cusp forms. But then there's talking about Dwork's Frobenius and its relationship with the U operator. And that's this next slide here. And so, again, it's technical, and I just want to give you an overview of what it is, not what it actually is. So let me skip the diagram for a second and go down to this right here. The L function of the k-symmetric power can be written as 1 minus alpha t of H1. H1 here is the p-adic cohomology, and alpha here is Dwork's Frobenius. All right. Now, to be more explicit, this H1 here is a quotient space by L over Lk of L, some operator acting on L. L is a space of p-adic functions, and Lk is some differential operator. It's a differential operator acting on L. So that's what this H1 is. And so now I just want to go up to here. That's what you see here is L. This is this p-adic function space. This is p-adic function space, and this Lk here. This lambda is the lambda modular map. And if you do the pullback of this and again here, this W is the Wronskian, this F is the hypergeometric function. And if you multiply these functions times this and do this pullback, you get this p-adic space of modular forms here, and the weight is negative k. And same thing here. If you do this map here, it goes into weight k plus 2.
That's an Eichler derivative.
That is an Eichler derivative, exactly. Exactly. And this diagram right here is basically Bool's identity, where you
Yes.
have, where you're plugging in minus k, you're taking the derivative k plus 1 times, out pops k plus 1 forms here.
Yes.
Exactly. So this is Bool's identity here, and then this commutative diagram right here is actually hidden away in one of Dwork's papers, in his I think it's his, yeah, it's one of his, yeah, cycles, I think cycles paper. If you unwind his stuff, you find this diagram. Again, you wouldn't see it. You would have to really know what you're looking for to be able to identify it. But there it is. That's one. And then two, sorry, I can't see this other side of the screen. Zoom, there we go. Right. So what this diagram does, this is a commutative diagram. And what this diagram does is it gives an isomorphism between Dwork's p-adic cohomology space and this space of a p-adic space of modular forms. P-adic space of modular forms. I'm not saying p-adic modular forms. I'm not saying that. I'm saying a p-adic space of modular forms. And here the D is exactly this Eichler derivative here. So that's giving a direct relation between the cohomology theory and some p-adic and some modular forms. That's one. And then the second thing here is on this side here, it is Dwork's Frobenius acting on these p-adic function spaces. That's Dwork's Frobenius. And on the right-hand side, we have the UP operator. Unfortunately, there's this -1 thing. That's because of the family that we live in. There's this -1. So you can just ignore that. But basically, you get this relationship between the Frobenius operator and this UP. And the horizontal arrows are isomorphisms. This is literally just multiplication. I'm multiplying this function times these functions here and doing the pullback of the covering map to the half plane. And so what this means is that these two here are they act in the same way, and so we get then that we get an equality of determinants. The determinant of this one is equal to the determinant, and not because right, but in a very direct way, which is what I was originally looking for when I was doing this. Right.
What is cap F again in that diagram? Remind me.
Say again. Sorry.
Your diagrams.
Yeah.
Something there called capital F.
Oh, right. So that capital F is the homogeneous. Sorry, not how much. It's the holomorphic solution of the Picard-Fuchs, and so it's F2.
Oh, I see. So that's a particular. I see that.
Very, very particular, and this Wronskian is very particular. I mean, it's Wronskian of the Picard-Fuchs, and this F is, yeah. So this is very particular for this one family.
Okay.
That's right.
I suppose there'd be one for the Hessian family and others, perhaps.
Right. And so that's actually my next slide. Is that what was happening when the Kloosterman was equal to p is equal to 2 or p is equal to 3? You know, why was that working? You know, why was there a relationship? So I want to mention that I do not know of a relationship. I do not know of a modular interpretation of the Kloosterman family when p is 5 or higher, right? I don't know of one. I don't even know how to guess at one. There's like 4 or 5 reasons of how things break down. I don't know which direction to go to see. But for p is equal to 2 and 3, it's very nice. And the reason is that the following happens. I only mentioned p is equal to 3 here. Same thing happens with p is equal to 2. When p is equal to 3, it turns out that the k-symmetric power of the Kloosterman, the L function of the k-symmetric power, is in fact equal to the k-symmetric power of an elliptic curve. And that's because of this expression right here, is that the number of FQ points or F3 points is equal to the Kloosterman sum here when P is equal to 3. And when P is equal to 2, exact same formula is true, but with a different elliptic curve. I'll just state right off the bat that if P is equal to 5, Kloosterman sums are real numbers, but they're not integers. And so you wouldn't even expect something immediate like this, because when P is 5 or larger, these are not integers, and so you don't have, integer can't be equal to this. So immediately, it wouldn't be so simple of a formula for P is equal to 5 or larger. There's more ingredients going on. So for P is equal to 2 or 3, you have this. And I have not gone through the details yet, but I suspect that the p-adic cohomology theory attached to the Kloosterman sums works in the same way as the above did. The Picard-Fuchs here is given by this information, is given by this differential equation here. It has a holomorphic solution at the origin given by F21 of 1656. There is a covering map here, and so here there's there's regular singular points that you can throw away. There's a covering map that you can define. Just like instead of using the lambda modular function, you can use this covering map instead. And I believe with this covering map and this holomorphic solution, then this type of diagram should hold as well for the Kloosterman family. For P is equal to 2 or P is equal to 3, something like that. And so here, for instance, I just want to mention that if you take this covering map that solves this quadratic equation in X and with the lambda modular function, and you plug that X into this hypergeometric function, out pops Eisenstein E4. Sorry, the fx to the 4th power is Eisenstein 4. So my point here again is that you're plugging in these covering maps into the hypergeometrics, and out pops modular forms. Right. So this is some future work that I'm looking into, and that's all I have. Thank you very much.
Thank you. So that looks like LSU.
That is. It is.
Okay. All right.
Well,